This is the video for sections 2.2 and 2.3 on using algebra properties in proofs. So this will be the first time that we see proofs in this class, but some of these properties should look familiar to you. The first set of properties we have are called properties of equality. Those are properties that you've been using in algebra to solve equations, to do things to both sides of an equation. The addition property of equality, for example, says we can add the same number to both sides. So if A equals B, then A plus C equals B plus C. Or if A equals B and C equals D, then A plus C equals B plus D. Since C and D are equal, we can add C to one side and D to the other. The addition property of equality lets us do that. Subtraction property of equality very similarly says we can subtract the same number from both sides. As you might guess, the multiplication property of equality says we can multiply both sides by the same number. So I'm not going to write that out. I'm just going to write multiply both sides. And the division property of equality says we can divide both sides by the same number. So the addition property of equality says we can add the same number to both sides. The subtraction property of equality says we can subtract the same number from both sides. The multiplication property of equality says we can multiply both sides by the same number. And the division property of equality says we can divide both sides by the same number, as long as that number is not 0, because we can never divide by 0. All those properties are properties you've been using to solve equations. If you had an equation in algebra with x and you were solving it for x, you would get x by itself on one side by moving everything else to the other side. The way you move it is to do the opposite operation. If it was added, you would subtract it from both sides. Well, the subtraction property of equality says we can do that. If it was 2x and you needed to divide by 2, you would divide both sides by 2, and the division property of equality is what says we can do that. So you've been using those properties of equality ever since you started algebra. The other ones you may not have explicitly used in algebra, but they're ideas that are not difficult to wrap your mind around. The substitution property says if A equals B, then either A or B may be substituted for the other in any equation. So if A and B are the same, you could plug B in for A in some equation, you could plug A in for B in some equation. We can do that because they're the same. So it doesn't matter which one we use, is essentially what that property is saying. The reflexive property says essentially something is equal to itself. A equals A. Pretty simple. But a simple idea that is used all the time, and we just don't realize we're using it. We just implicitly understand that something is equal to itself. The reflexive property puts that into a property form. The symmetric property says if A equals B, then B equals A. That equality works both ways. It's not just a one-directional thing, it's a bidirectional thing. If A equals B, then B equals A. It works two directions. The transitive property says if A equals B, and B equals C, then we have a chain of things. Since A equals B and B equals C, then it must be true that A equals C. Also pretty simple. A is the same as B and B is the same as C. That means A and C must be the same. Now, congruence is another way that we can relate to quantities, to numbers, or to segments, or to angles, or to triangles. They can be congruent if they are the same size and the same shape. So, the properties of congruence follow from the properties of equality. And they're saying roughly the same thing, just with congruence instead of an equal sign. And the symbol for congruence is an equal sign with what's called a tilde over it, or a squiggle over it. That means congruent. So if you see that symbol, think congruent. It means things are the same size and the same shape. So the reflexive property of congruence says, for example, segment DE is congruent to itself, segment DE. Or angle A is congruent to angle A. Something is congruent to itself because it's clearly the same size and same shape as itself. That makes sense. It seems weird that we have to state that, but if we don't state it, we can't use it. The symmetric property says, just like it did for equality, congruence works both ways. It's a bidirectional equivalence. If segment DE is congruent to segment FG, then segment FG is congruent to segment DE. That we can go both directions just like we can with a regular equal sign. Similarly, if angle D equals angle E, then angle E equals angle D. So it works the same for angles as it does for segments or for any shapes that we're calling congruent. And the transitive property of congruence says, for example, if segment DE is congruent to segment FG and segment FG is congruent to segment HI, then we have a chain just like we did with the transitive property of equality. Segment DE must be congruent to segment HI. Since DE was the same size and shape as FG, and FG is the same size and shape as HI, then DE must be the same size and shape as HI. Okay, now the reason we have all these properties and we state these properties is because we want to use them. And we use them in things that are called proofs. Proofs are logical arguments that something is true. And those logical arguments are always justified with reasons. The reasons are often definitions, properties, or postulates. Remember, we had postulate at the beginning of the unit when we said a postulate or an axiom is something that is assumed to be true without proof. So we assume it to be true so that we can use it to prove other things. So we're going to look right now at one example of a proof, and we'll do a couple more examples in class. A proof will always give you a given statement, something that you are given to then work from, a place that you start from, and then it will always give you something that you want to prove. So it gives you where you start and where you want to end, and you have to figure out how you get there. So we start in this proof with two segments, segment RT and segment PQ. And we're told in our given statement that segment RT and segment PQ are intersecting at point S so that RS equals PS and ST equals SQ. So we can see that in the picture here. We have segment RT and segment PQ. They intersect at the point S, and the single hash marks show us that RS equals PS, and the double hash marks show us that SG equals SQ. Remember, the hash marks are a way to denote how things are equal in our diagram. Okay, so here is one way to do a proof. This is called the two-column proof. First column is always called statements. Second column is always called reasons. In each column we're going to list each step of our argument that gets us from where we started to where we ended. So the first thing we do is we state where we're starting. So we state the given. And our givens are that RS equals PS and SG equals SQ. So that's our statement number one. It's actually two statements that are together. We can do that if we're using the same reason for them. And our reason will always be first given. We know those things because they're given. The reason is always an explanation for why we know the statement is true. We know RS equals PS and SG equals SQ because we were given those in our problem. Okay, number two. Statement number two will have its own reason. The reason will be how we know that statement is true. Well, if RS equals PS and SG equals SQ, then I can state RS plus SG equals PS plus SQ. Now, why can I do that? Well, look what I did. I have RS equals PS from here, and then I'm saying SG equals SQ, so I can put SG on one side of the equation and SQ on the other side. That looks very familiar from one of our properties up here. This one right here. If A equals B, then A plus C equals B plus C. Or if A equals B and C equals D, then A plus C equals B plus D. If I have two sets of things that are equal, I can add one element to the second one to the left side and one to the right side, and I still have an equation. That's the addition property of equality. So, my reason then is the addition property of equality, and we can abbreviate property of equality in this class as POE. So I know this is true because of the addition property of equality. That says I can add the same thing to both sides. Since SG and SQ are equal, I can add SG to one side and SQ to the other. Statement number 3. If I have that RS plus SG equals PS plus SQ, then if I look at my picture, my goal, remember, is to say something about RT and PQ, to say that those are equal. So far in my proof, I haven't used RT or PQ at all. I need to work those in somehow. My picture gives me a hint on how to do that. RT is RS and ST combined. Okay? So let's write that down. RS plus ST equals RT. Now, how do I know that that is true? How can I write that? If we look back at our notes for the first video we watched, that is called the segment addition postulate. That if two adjoining segments sharing an endpoint, if those are added together, we get the whole segment. RS plus ST equals RT. Well, we can make the same statement about PQ, that PS plus SQ equals PQ. So let's do that. Since we'll use the same reason, the segment addition postulate, we're going to include that within statement 3 rather than writing it as a separate statement because we're using the same reason. So PS plus SQ equals PQ. Again, by the segment addition postulate. So those two statements together are statement 3 because they share the same reason, the segment addition postulate. Now we're almost there. Remember, we wanted to say that RT equals PQ. Well, we know that RT is RS plus ST, and PQ is PS plus SQ. But if we look at statement number 2, right here, we've said that RS plus ST is the same as PS plus SQ. Well, if RS plus ST is also RT, let's fill that in down here. So I'm essentially rewriting statement 2 using what I know from statement 3. RS plus ST is RT. Well, what is PS plus SQ? That's PQ. So since RS plus ST equaled PS plus SQ, and RS plus ST was RT, and PS plus SQ is PQ, I'm replacing this with this, replacing this with this. And that tells me that RT equals PQ. What allows me to make those replacements, or those substitutions, is the substitution property. If two things are equal, I can plug one in to an equation for the other. So I can plug in RT into this equation for RS plus ST. I can plug PQ into this equation for PS plus SQ. We ended up where we wanted to end up. We wanted to show that RT equals PQ. It's exactly what we said in our last statement. So our proof is done. That's one way to write a proof, and we may look at another way soon in class. Proofs will seem intimidating at first, and it probably seems intimidating right now, but the more you practice it, the more you get a handle for what's going on, and the easier it should become. So we're starting out slow. That's the first proof we've done, and we'll take it slow as we go through. Section 2.3 gives us two theorems that are useful, but that seem straightforward. The midpoint theorem says that if M is the midpoint of segment AB, like I've drawn in the picture here, then AM is 1/2 of AB. Seems right. If M is the midpoint, it divides AB in half. So AM should be half of AB, and it also says MB is half of AB. So a midpoint is dividing a segment into 2 halves, is essentially what the midpoint theorem tells us. Okay? We will review a proof of that in class. We'll look at that in the book. But that's saying a midpoint divides a segment into 2 equal halves. 2 smaller segments that are half of the whole segment. And very similarly, the angle bisector theorem tells us if we have a ray that bisects an angle, so if ray BX is the bisector of angle ABC, then angle ABX equals 1/2 of angle ABC. So this angle, angle ABX, is half of the whole angle, and angle XBC is half of the whole angle. Angle XBC equals 1/2 of ABC. So it's saying an angle bisector cuts the angle into 2 halves, 2 smaller angles that are half of the whole angle. It's exactly the midpoint theorem, but with angles now. So instead of a midpoint, we have an angle bisector. And again, we'll look at a proof of that in the book in class. And now your immediate practice problems. So please write out both of these statements at the end of your notes, and then write your answer. Your directions are: justify each statement with a property that we just used in this video here. If RS equals TW, then TW equals RS. So you write underneath that the property that tells us that is true, that when RS equals TW, TW equals RS. Just write the property stated. And number 2, if 2x minus 5 equals negative 3, then 2x equals 2. So write down the statement, or write down the property that tells us that statement is true. Okay, just write it down. And that is the end of sections 2.2 and 2.3.